let's talk let's talk about how to plot specific attributes of a simple feature object. By default, you can use the plot function to plot all the attributes of an SF object, but in general, this isn't very helpful because oftentimes our SF object has many different attributes. So in this case, if I take the COVID_US SF object that I created earlier and I use the plot function on it, you see it plots all these different, it creates a plot for all the different attributes, or at least the first 10 in this case. And there are 17 total attributes, and it says you can change an argument to plot them all, but this is kind of messy. It's hard to see what's going on. There's no color scale, and so this is probably not very useful. So more likely than not, you're going to want to plot a single attribute or variable, which can be done by subsetting that variable in your SF object and then plotting the subsetted object. So to illustrate that, let's plot the land area of the states, though I'm going to exclude Alaska and Hawaii just because that creates problems over here with making this map really big and really wide. And we've already learned how to constrain this, but this will just simplify the subsequent plots. So we're gonna do that. So using the pipe operator here, I'm gonna pipe COVID_US into the filter function, and I'm going to retain all the rows where the STUSPS column values are not either Alaska or Hawaii. And I'm going to save that filtered object as COVID_US. And now I use the plot function on the subsetted COVID_US object where I subset the land area variable, and I get the plot here. And I'll be honest, I don't like this color scale at all. I think it's bright, it's distracting, and these colors, well, you can use them to distinguish the different levels. There's not a nice natural ordering to it, at least in my opinion. So the question is, I guess, how can we change some of these things? And so we'll talk about that briefly. One of the things that's not very useful about this particular plot, and something to think about when you're plotting spatial data in particular, is that in this case, each of the states literally has different amount of land. There's different area depending on their size, and so the land area, because these states include both land and water in different locations, this is going to be directly related to the size of the state. And so it's not very fair for a place like Texas because it's so much bigger in comparison with a state like Rhode Island. So if we wanted to compare the proportion of a state that was water, for example, compared to the total area, which I'm assuming is the land plus the water area, then we can create a new plot. So what I'm going to do here is I'm going to take the COVID_US data frame, I pipe it into the mutate function of the dplyr package, and I'm going to create a new variable, prop_water, which is the proportion of water, and it is the water area of the state divided by the water area plus the land area. And I'm not sure if this is actually the entire area of the state, but it's probably pretty close. And what I'm going to do here is that I'm going to save the new object with the new variable as COVID_US. So I've essentially just added that column. And now I'm going to plot the prop_water column of COVID_US. And the nice thing about this is we can now compare all the states because we're looking at the proportion of the water, not just the total amount of water area. And you can see that when we do that, we get very different results. Texas is no longer one of the states with the largest values. In fact, it's clearly Michigan in this plot. And then we have some other states like Louisiana, Florida, Wisconsin, and some of these coastal states here that seem to have a higher proportion of water in comparison with many of the other states. If we wanted to see the exact states that had the largest area, the largest proportion of water, because this is just a fancy data frame here, we can use some other dplyr functions. So in this case, I'm going to pipe COVID_US into the slice_max function, which will figure out what the maximum rows are according to some variable, which in this case is prop_water. I want the 6 rows of COVID_US that have the largest values of prop_water. And then just to make this graphic a little nicer, I'm going to only select the name column and the prop_water column, the attributes really, because you can see the geometry list column is going to be retained. And when we do that here, we see that Michigan is the highest. It has over 40% water. Rhode Island is actually the second. So previously I mentioned comparing Texas to Rhode Island. Well, Rhode Island actually has a very high percentage of water, at least according to this particular data set. And we have Massachusetts, Maryland, Delaware, Florida, etc. So you may be wondering how to change some other aspects of this plot. So for example, you might want to change the number of breaks here, so the number of colors that we use in this color bar, and you really might want to know how you change the color palette. So that's what we're going to talk about next. So to change the number of breaks, you can actually just use the in-breaks argument. So that's pretty straightforward. To change the colors in our color bar, you want to specify the pal argument. And this can be a little bit more complicated, so we're going to go into this in a bit more detail. So the pal argument takes a function that, when given n, the number of desired colors, or the number of breaks plus 1, I believe technically, it's going to return a vector of colors. So it actually gives you colors. That's what the function is supposed to produce. And as I mentioned previously in this tutorial, there's a bunch of functions in the graphic or GR devices package that will do this. HCL.colors, rainbow, heat.colors, etc. These all have a lot of they're all color palettes. These ones right here, these ones would work straight away. If you just put in n, it's going to give you the colors, that many colors. However, the HCL.colors palette, or that function, works a little bit differently because it's actually more of a generic function. So the HCL.colors palette it's a particularly good function because it includes color palettes like viridis and kividis, corrected viridis, that are particularly well suited to displaying colors that are friendly for individuals who are colorblind, and also can be easily understood when printed in black and white. So there's actually some cool theory behind these color palettes. I'm not an expert in them, but I do know that they're good choices if you are displaying data in general. But because the HCL.colors function is kind of a generic function, you're going to have to be a little more creative. So there's actually a palette argument inside the HCL.colors function that's going to indicate the exact color palette that you want to use. And so in order to use this in the plot function for an SF object, we're going to have to create a custom function. And so we're going to have to create a special palette for viridis, a special palette for kividis. And so I'll just describe this function here. So viridis underscore pal here, it takes the argument in, which is going to be the number of desired colors. And this function actually just calls internally the HCL.colors function. It will request in colors from that function for the viridis palette. And really the key detail here is I specify palette equals viridis inside this function, because if I just use HCL.colors directly with my plot function up here, for example, it's going to throw me an error because it's not going to know what that palette should be. Actually, I think it will work because viridis is the default. But if I wanted a different palette, I would actually have to specify something else. So I'm going to do the same thing for kividis, and I'm going to create kividis underscore pal. This function takes in the number of desired colors, and it calls the HCL.colors function. It requests in colors, and we want the palette to be kividis. If you want to see these colors, here's just kind of a hackish approach to quickly showing this using the image function that's available in base R. And so I pass in this matrix of values. I specify 5 colors from the viridis underscore pal function, and then these are the colors that are returned. So this is the viridis color palette with only 5 colors, and we can do something very similar with the kividis, the corrected viridis palette, and we get these colors right here. So I actually personally find this to be much more visually appealing, though supposedly this is actually a better color palette in terms of being colorblind friendly. So it's kind of up to you about which one you use. They're both really great. So let's actually do some analysis of the actual COVID-19 data that we have in our COVID_US SF object. To make it most useful, I am going to create a new column called death_rate_100K, which is going to be the number of confirmed and probable COVID-19 deaths per 100,000 persons in each one of these states. So similar to what I have done before, I pipe the code_US data frame into the mutate function of the dplyr package. I'm going to create a new column, death_rate_100K, and that is going to take the deaths column, divide it by the population column, and then multiply it by 100,000. And by doing that, we get the desired column. And the reason we actually convert this to a rate is because that makes it easy to compare the number of the rate of deaths in the different states. Because if we only looked at the number of deaths, then most likely the bigger states like California, New York, and Florida, Texas, those states are going to have a higher number of deaths simply because of the sheer population size. If we want to see which states have the highest and lowest death rates, at least based on this data set at this point in time, then we need to standardize the values to a common scale. And that's what we're doing here. And this is very important when you're plotting spatial data. Make sure you're plotting a variable that you can actually compare across the different states. If you don't standardize them so that they can be compared directly, then your graphics are not going to be very informative. So we create this variable and we store it, the updated object, in COVID_US. And now I'm going to plot the death underscore rate underscore 100K attribute of the COVID_US simple feature object. I only want 5 breaks. I don't want too many colors here. So 1, 2, 3, 4, 5 breaks. And then I'm going to pass it viridis underscore pal, that custom color palette I created above. And so when I do that, I get the following graphic right here. And what we can quickly see here is it looks like from this particular data that actually Delaware has the highest total death rate per 100,000 persons. And some of the other states that kind of jump out, I guess, are Louisiana here is pretty high. We have Alabama, got New Mexico over here. And so there's a number of states that definitely have higher rates than others. One of the states with the lowest, or it looks like the lowest based on this particular plot, is actually Vermont. And so Vermont has a rate of fewer than 50 deaths per 100,000 people, at least cumulative up through this time. And so you'd have to look at this data set to understand more about what we're doing here. We're not trying to interpret these plots in great detail, but based on this, we can see which states have the lowest death rate per 100,000 persons and the states with the highest number of deaths. And then below, I'm actually going to create the same graphic, except for the fact that instead of using the viridis color palette, I'm going to use the kividis color palette. And so I just changed pal to kividis underscore pal, give it that function, and we get the same plot as before. We're just using a slightly different color scheme.